The relationship of the magnetic field to moving charge is fundamentally a three-dimensional phenomenon. We want to represent this three-dimensional phenomenon in two dimensions sometimes, though. So it's conventional to use x's and dots as vectors. The way that x's and dots work is not only do we have vectors which point in the positive x direction and vectors which point in the positive y direction, we can also have vectors that point right out of the page. To make these vectors, what we'll use is a circle with a dot in the middle. The dot is supposed to be like the point of an arrow that's pointed at you. If we look at it in three dimensions, and let's say that here is a tabletop with a piece of paper on it, then the positive x direction will point along the paper. The positive y direction will also point along the paper. But the positive z direction now points up off the paper. That's the idea. And since we are looking down on the problem, the arrow of the positive z is pointed directly at our eye. And that's what this circle with a dot represents. An x, on the other hand, is going to be a vector which points into the page. So that would be a vector pointing in the negative z direction right now. What we want to do is we want to draw the magnetic field around current carrying wires. So it was discovered a long time ago that a current carrying wire can deflect a compass, which means that the magnetic field and current were somehow inseparably related. Today we use a right-hand corkscrew rule to show the relationship between the magnetic field and moving charges. The thumb points in the direction of current, and then the fingers will curl in the direction of a magnetic field that's created around a current carrying wire. This is the magnetic field that we wish to draw down here. Let's start with the example where the current is pointing toward us, toward the viewer. Because of the dot, current points out of the page. So what exactly does this mean in three dimensions? Well, it would be as if there was a long, thin wire coming right out of the page that's protruding out of the page. And the direction of current is toward the viewer. That's what it means when we look at a two-dimensional page and see a dot. So what gets created in this situation? The magnetic field that's created will form concentric circles like this, where the field is always directed counterclockwise. and the field spreads out from there, going in the same counterclockwise direction. Let's represent this idea with concentric circles showing the magnetic field lines that are created by this wire. And we want to show the direction as well. And the field is actually going to keep going to infinity but we can stop there. What about when current is flowing into the page? What would that be like? So when we see a dot inside a circle, that means that current is flowing out of the page. And according to the conventional directions of X being to the right of the page and Y being toward the top of the page, then this would be the positive Z direction that current is flowing in right now. However, when we see a circle with an X inside of it, what that means is that current flows into the page. Some people think of it like an arrow with feathers. And when the arrow is traveling away from you, you can see the feathers. And so the X is supposed to represent the feathers. This would be the negative Z direction. Okay, so can we represent that situation? What I'll do is I'll draw a new eye. And a whole new piece of paper. The positive X direction is to the right of the page. The positive Y direction is toward the top of the page. And then the positive Z direction would be off of the page. We're going to again want a wire that's cutting through our page here. The difference this time, though, is that current is going to be flowing in the negative Z direction. And when that happens, the direction of the magnetic field switches. We're still going to have concentric circles, but the field will be oriented clockwise this time. So it'll look like that. Let's draw that idea here. When current is pointing into the page. We want concentric circles. But this time, according to the right-hand rule, we will reverse the direction. You want to imagine in your mind grabbing onto the wire and letting your thumb point into the page this time. And then how do the fingers curl? They would curl clockwise. You would take the situation that's shown here and reverse your grip on the wire so that the thumb points downward and then the fingers curl in the opposite direction, the clockwise direction. Now, what would be something that we can observe that would tell us what the direction is? Well, one thing we can do is we can place compasses around the wire. So let's say, for example, I was to put a compass here. What direction would the needle point? Well, the compass always points in the direction of the magnetic field. So it should point upward. What if I have a compass that I set down right here? What direction would the needle point now? Now it would point to the right. Okay, if I put a compass next to this current carrying wire, we see that the field is directed up at this position, so our compass would tend to point up as well. And what if we place a compass here? Then the direction will be to the right. This idea is shown in this diagram here, where at first there's no current, and at that time the needles just all point toward geographic north. Once the current is switched on, though, what we'll see is that the compass directions will be changed, they'll be deflected, such that they follow a circle around that wire. You can even see here how iron filings with magnetic properties will orient themselves and align with the magnetic field lines. All right, so that's wires going into and out of the page. What do we do when we're looking at the side of a wire, though? This is a wire that carries current in the positive X direction. Well, the same kind of phenomenon is going to happen. We're going to get concentric circles around that wire. Okay, now how do we show this, though, in 2 dimensions? Because in 3 dimensions, interestingly, in 3 dimensions, it would be much easier to show. If we're looking at the side of a wire, and let's say that the current is going in the positive X direction, then we would try to grab the wire with our hand such that the thumb pointed this way, but our fingers would end up wrapping around like this. And this would also tell us the direction of the magnetic field. So the magnetic field would be going this way. In loops around the wire. Okay, but we want to show this not in 3 dimensions, but in 2 dimensions. So imagine that we've got a plane now. And we don't want to show what's happening out of the page and in front of the page and behind the page and all that. We just want to show what's happening right here. And so to do that, we're actually going to use dots, because dots mean that arrows are coming out of the page toward our eye. And down here, we're going to use X's, which means that the field is going into that page. Okay, so all we care about is that field is coming out of the page at the top of the wire, and field is going to be going into the page at the bottom of the wire. That's the idea. So what we want here is we want dots. It tells us that the field will be pointed out toward our eye, and the field will be pointed in away from our eye at all points below the wire. The magnetic field does have a variable that's associated with it, and we're going to call it B. B is the magnetic field. If you recall, the electric field had the letter capital E. The magnetic field has the letter capital B. So what would the magnetic field look like for this wire when the current is pointed to the left? Imagine grabbing the wire with your right hand and letting your thumb point to the left. Then which direction would the field be going at the top, and which direction would the field be going at the bottom of the wire? The fingers tell us that. And so what's going to happen is it would be switched, where we'll get X's on top. Fingers would go into the page there, and then they would come out of the page at the bottom. So that would be a good drawing of the magnetic field around that wire. All right, let me try to draw this in 3 dimensions to give you an idea of what I mean. Okay, so as you can see, the fingers are pointing into the page on top of the wire. But when you get to the bottom, they're pointing out of the page. So we use dots on the bottom of the wire then, and we use X's on the top. Try drawing the magnetic field for yourself on these 2 wires down here. The hint is you're going to need X's and dots. Okay, so when grabbing this wire, here's our thumb. Our fingers are going to curl around, and our fingernails will be visible there. what we're going to want is we're going to want dots on this side. And X's on this side. This is because our magnetic field lines in 3 dimensions would look like this. So it's into the page on the right and out of the page on the left. For the other diagram, we would switch our hand such that the thumb is over here now. And as we can see, our fingers will be pointing into the page on the left side of this wire, but they would point at us on the other side. So what we're going to want then is X's over here. And we'll have dots on this side. It's the opposite of what it was when the current was pointing up. That's the magnetic field around a current carrying wire.